Works now? Okay, sure. So welcome everyone to join today's seminar at the University of Iceland. So this seminar is organized by the Electrical Power System Laboratory at the university. I'm Zhao Yuan. So the title is Society Scale Decarbonization, where electrification and electricity market perspective. So today we have a very great guest professor, Yury Dvorkin from the University of the New York University. He will soon transfer to Johns Hopkins, right? So Yury is an incoming associate professor at Johns Hopkins University with cross appointments at the Department of Electrical and Computer Engineering, Department of Civil and Systems Engineering, and also Ralph Cornell Sustainable Energy Institute. So before joining JHU, Yury earned a PhD degree at the University of Washington. Yury's selected honors include the 2016 Scientific Achievement Award from the University of Washington, 2019 NSF Career Award, the 2019 Goddard Junior Faculty Fellowship from the New York University. He's also being selected as an invited participant and presenter at COP26 in the year of 2021, and also in the Arab American Frontiers Symposium in 2021. So I would say Yury have been my friends for several years, and every time I read his work, I'm very impressed by his methods, his derivations, and also his very unique and innovative concepts and methods to solve electricity market issues and many other issues. I think it's a very great honor for us to have Yury here to give us a talk. So let's welcome Yury to start the talk, please.
Thank you. Thank you so much, Zhao. And the honor is all mine to visit Iceland, to be here with you today. And thank you for going into the trouble of organizing this seminar and all that it comes with. It's much appreciated. And just as a side comment, because I'm going to be talking about decarbonization and electrification, I've been able to see a lot of progress here in Iceland, and the United States has a lot to learn from you folks. It's a terrific amount of effort that your country put into this particular sector, and it's so joyful for me to see how it pays off and what kind of amazing opportunities it provides. But I'm going to be talking today about the power grid and electricity market perspective on the society scale decarbonization, which is effectively a way to drastically change the way our society operates, in particular as far as it concerns the use of various kind of energy forms. And one particular strategy that my research is focusing on is electrification, basically how we can replace the use of fossils with electricity. And of course, none of this work would have been possible unless it was for this brave team of postdoctoral scholars, master and PhD students that work with me. They are basically the inspiration and the drives behind every research project. We work in a very multidisciplinary fashion, but the core expertise that we have is, of course, in electric power engineering, and we borrow concepts from operation research, economics, in order to deliver policy and environmental impacts. The research areas that the group works on, of course, the core activities are related to stochastic electricity markets and energy economics more broadly. We develop energy analytics methods for smart grids. We look into power grid resilience and cybersecurity, as well as we are recently looking into how to take these methods and to transition to fully electrified, decarbonized society. And more recently, we started looking into the energy and environmental justice issues, because as the energy transition accelerates, it becomes more and more important to see how it would unevenly affect our society, and try to understand where these imbalances are coming from, and try to level the benefits of these technologies across different population groups.
Really?
Yeah.
The previous slide you show us there are many areas you cover, from operations research, engineering, economics, policy, ecology. So how you break through, I mean, the methods, the topics from different areas and integrate them together to this market perspective of renewable energies? I mean, this is very, I mean, broad areas, I think.
In our case, it's all application driven. When we look into a particular energy problem and we realize the traditional skill set is not fully capable of addressing the issue, we're trying to branch out to other domains and see what's been done in there in order to understand what we could borrow and adapt and develop for our particular field. In particular, one important issue for us is the mechanism that understands the risk, right? And I'm going to be talking about that for later. For many years, energy markets and electricity markets have been extremely they've been deterministic with no understanding of risk or uncertainty. On the other hand, there is an entire domain of financial engineering markets and financial markets that have been dealing in the area of risk with a profound exposure. So naturally, when we wanted to think that renewables will play a greater role, but they will also introduce uncertainty and risk into market operations, it was only a natural connection for us to make and to go and see what financial engineers do in order to see how these techniques could be applied in the electricity market context.
I see. Yeah, great.
Thank you. And the motivation for our current and future work, it comes from essentially two sources. I would like to start with the quotes from two men. The first one is Bill Gates, who once was the richest man on earth, and recently he published his book on climate change. And the Bill Gates recipe on how to avoid the climate disaster has 4 steps. The first step is very simple: electrify everything that you could electrify, and that includes industry, transportation, buildings, whatever can be produced with electricity should be produced with electricity rather than with any other energy carrier. Then you supply clean electricity from renewables from the power grid, and that should help you to drastically cut your emissions. But at the same time, there is a realization that you will not be able to fully cut the emissions, and there are going to be some residuals that you have to burn some natural gas, for example, in order to produce some kind of plastic, which is rare. In this case, you have to use carbon capture to offset these emissions. And of course, the 4th step is to use materials more efficiently. So basically, the idea is very simple: electrify whatever is possible and use clean electricity to supply that energy carrier to make sure that you don't emit CO2. The second man I would like to quote is former Vice President Al Gore, who 24 years ago said that no particular technology will address climate change, and we have to invest in a portfolio of technologies that would support decarbonization. And despite the fact that he said it 24 years ago, that has not been resolved yet. The issue of climate change is still pending. Please don't blame me. Back in the day, I was not an American, so I didn't have a say in the 2000 elections. But if we look into the modern profile of America, and this is the most recent data that I have from EPA from 2019, we will see that all the emissions that we have in the country, they come from essentially 5 sectors. The largest one is transportation. Then we have the power sector, then we have industry, heavy industry here, and then we have commercial and residential buildings as well as agriculture. So the point here is that in all of these sectors, right, we will have electrified technology that could replace the use of fossil fuels. For example, in the electrified transportation, we have electric vehicles. We have these vehicles at an affordable price that a middle-class American family can afford buying. In terms of the power sector, we do have renewable electricity. In terms of the industry processes, we're a little bit behind, but there is a lot of pressure to electrify industry, and that has some good examples. For example, aluminum, it's already a heavily electrified process, aluminum production. So we're looking into different ways to electrify production of other chemicals. And the chemical sector is one of the largest and most polluted sector of the national economy. And there is, of course, a lot of push towards electrification of buildings, because right now natural gas and oil are the primary sources of heating in the United States, but electrified heating and cooling is far more efficient and getting more affordable. So in that particular...
One question, isn't Bill Gates forgetting about geothermal energy?
It's a renewable source of energy, so he's not forgetting about it. But
it's not electrifying the heating. It's
yeah.
Using geothermal is not electrifying.
Yeah, yeah.
Well, partly, if you use these, what's it called, heat exchangers, that you drill a hole in the earth and put something, and then you start, having an inverse refrigerator. Actually.
Yeah, it's a very important and I must say a very pleasant source of heating, which I enjoyed a few days ago, not far from here. But yeah, that's very true. Basically, replace the use of fossils with anything that would produce the desired energy, right? And we have projects in some of these sectors. For example, as I said, we have electrified technology to satisfy transportation needs, but the bottlenecks are related to EV charging. So we need to make sure that we have sufficient number of EV charging so that access to this infrastructure does not prevent people from adopting electric vehicles. In terms of the electricity sector, the key bottleneck is to have a risk-cognizant electricity market, something that I'm going to talk at length later today. In terms of the electrification, we're trying to design methods that will help us to power chemical processes using clean electricity. And for buildings, we're trying to understand better what their energy needs are and how they could be supplied in a way that would help us to reduce the impact on the power grid when they're fully electrified. One important thing that we realize is that as we get society addicted to electricity, we have to be responsible because in this case, the more addicted the more dependent our society on electricity, the more vulnerable it becomes in case of natural disasters, which are fairly common, especially in the United States. So we need to make sure that the infrastructure that we develop is resilient to this kind of events, and at the same time, if any disruptions occur, right, we have ways to minimize disproportional effects on the society. A particular resiliency risk that we are looking into is the cybersecurity threat, which is a very cool project I'm working on with a few colleagues. And it's a particular ordeal to talk about cybersecurity issues of American critical infrastructure systems with my accent. So in this particular setup, right, from this portfolio of projects, I'm going to focus on electricity markets. And the reason why I'm going to focus on it is because markets are fundamental binder. It's essentially a glue to the power system operation these days, and they are run in a completely deterministic manner right now with some very myopic realization of uncertainty. What we need to do is to make sure that this myopic representation of uncertainty does not trickle further, because in this particular case, it would cause even greater inefficiencies as more renewables come up. So the motivation here is that renewables are intermittent, and we need to have a way to deal with this intermittency. So while the sources for this intermittency are various, right, we're going to focus primarily here on the sources that come from renewables. And the idea is very simple, that as long as you have a deterministic market and market participants are intermittent, they will take advantage of it, because they will effectively have a way to gain the market. So what we essentially are trying to achieve here, we're trying to change this market box in a way that it will provide the feedback to market participants in the form of outcomes which are uncertainty dependent, but at the same time, it will provide an interface this link for the market participants to submit the strategy, which is going to be cognizant of their own evaluation of uncertainty. And the idea here is very simple, that the system and the market participants will have very different estimates of the uncertainty 1 and uncertainty 2, so that if the market is designed properly, eventually over several iterations, they will reconcile their vision of uncertainty and will help to narrow the gap. Yeah, sure.
So you are mentioning the uncertainties from the forecasts. So we have the uncertainties of the forecasts for many sources, like the forecast of the demand and the forecast of the renewable energy generations. Which source of uncertainty do you think is more dominant in the power system operations?
Right now in the United States, it's already uncertainty of renewables. Yeah, it's more and more evident that renewables are becoming far greater source of uncertainty than demand. I mean, with demand, you can have a fairly large forecasting error, one-off error, but it's always easy to control and manage, unlike renewables, because renewables exhibit unpredictable patterns. And if you look into the past events, right, you will see that large power outages have been primarily caused by renewables rather than intermittency of renewables, or complicated events which interbind both renewables and conventional technologies rather than by something on the demand side.
I see. We know that the demand forecast, the uncertainty, I mean, the errors for the predictions can be minimized or reduced if we consider large-scale system compared with small-scale system. So the load predictions for large power system is more accurate than small system. So do you think this will also apply to the renewable energy predictions?
There is some role, a correlation between different renewable sites. But within a small location, yes, but for a larger system, it's going to gross out eventually.
Okay.
And basically, the solution that we envision is that if we have a way to parameterize uncertainty, we will have a way to map it into risk that both market participants and the system could analyze. And when we're talking about the risk, we're essentially talking about both physical risk and its mapping into financial risk. A physical risk being, for example, constraint violation or some kind of physical edge. With financial risk, we're talking about, like, you know, some kind of shortfall that comes from the financial risk. And the important piece of our work is in understanding that both uncertainty and risk can be connected to one another using the notion of variance, which is a mathematically convenient construct to evaluate both. And at the same time, it's connected at a higher level with various risk measures and security products and their pricing. So essentially what we're devising here, we're looking into the uncertainty, how it maps into risk, and how risk mapping can lead to security trading. So a very simple illustration that would show why variance is needed is shown here. What you can see on the slide, it's a dispatch of different generation technologies, and they're shown here with different colors. For example, this color up here, it's natural gas. The purple color is nuclear. The red one is hydro. The blue one is coal. These are different generators dispatched across the day to meet the black line, which is the load forecast in New York ISO. Right, and that's a current practice which essentially has a deterministic black forecast, this line, and we basically schedule our generators ahead of time to meet this forecast.
The RFO, I mean, the legend, it means oil?
Yeah, RFO means oil, yeah.
So this is for the New York State? Yeah,
New York State, New York ISO system. But basically, when we see some deviation from this forecast, right, when we stress the original day ahead schedule, we will see that actually a lot more flexibility is needed to accommodate various peaks. And that precisely means that we will have to dispatch RFOs, which are the oil generators, and they are fairly polluting, and we'll have to dispatch natural gas. The problem is that while this is the normal scheduling which market does, and this is a potential realization, right, When we are at the day-ahead stage, we don't know the realization yet, so we have to assume many scenarios that will happen. And what you can see here, you can see options from 1 to 10, which represent different scenarios of what the future may like. And the difference between those scenarios, it shows you the variance, right? That may happen relative to this normal forecast that the market currently accounts for. So the idea is very simple. When you have these 10 scenarios with different stress deviations from the forecast, what if we take this normal scenario in here, and while producing the dispatch for this scenario, we take into account potential variances? And in this particular setup, the reason why we want to account for these variances is because each particular scenario from the previous slide, it will lead to different cost impacts. And here is just a sample for scenarios 3, 6, and 9, which I randomly chose. And you can see on the bottom slide that they would lead to different electricity prices in different locations, where red indicates higher prices and blue indicates lower prices. So a small deviation from the normal scenario will cause very different prices between case 3 and 9, right? And this is a kind of changes between scenarios that we want to be able to account for proactively. And the point here is that we need a systematic way of accounting for this variance, which is not currently internalized in the market and cannot be done in a Thoring way. But the thing is that these issues will become even more prominent in a few years when we will finish the construction of the offshore wind parks. And here you can see, over here you have New York City, and these are different offshore wind sites of the coast of Long Island, which are gonna build around 4 gigawatts of capacity. And this will start, in total it will be 9, but for now it's only 4. And this will be building up fairly quickly, and they will start showing up in the market quite shortly.
Can we cover all the wind farms after the installation? Can they cover how much percent of the load they can cover?
For comparison, a typical load here is about 30. It's actually a peak day here we're analyzing. It's about 30 gigawatts. So when 9 gigawatts is constructed, it's going to be about a third of the system.
That's a lot.
Yeah, that's quite a lot. So in this particular case, we started looking into the potential way to parameterize the uncertainty that will come from this fleet. And basically what we were able to do, we were able to leverage data that is available through NREL. And this data has 26 features, which represents different environmental variables that affect production of offshore wind power plants. And we noted that some of this data is well correlated. As you can see here, you have a correlation matrix between the features, where the yellow color shows one correlation, basically perfect correlation. So basically the idea came from mind that, like, okay, if we have so many features and we want to predict, like, the way how offshore wind power would behave, why wouldn't we find a compressing way to represent it? And we ran principal component analysis just to see which features matter. And we were able to show, based on the eigenvalues, that about 3 features matter, right? The first 3 components. Then,
for the correlation in the previous slide, this correlation amongst the features. So if I'm correct, for example, for feature 25, and then we have feature 1, let's say feature 16, then the correlation number, the index is 1, right?
Yeah. So it means they're good correlated.
Okay, so let's say the feature 16, the meaning is wind speed at 20 meter. And then feature 25, that's wind speed at 200 meter. So it means they are strongly
correlated. Yeah. But on the other hand, for example, if you can see like relative humidity, feature number 2, right? And for example, feature number 3, air temperature, right? They are less correlated. Their correlation factor is 0.6. So some features matter, some features don't matter.
So this is for one wind farm, or this is?
That's for each location. Yeah, we ran this analysis and validated it for different locations. Yeah. So basically, the idea is now, given this, how do we obtain the variance? And the key feature here is that transformation of wind speed into wind power is heavily nonlinear. It's driven by the wind turbine curve, which is shown here on this slide. It has a cut-in, linear, saturated, and cut-out ranges. And an important thing that we came up with here is that we were able to convert historical data that we have in essentially a Markov process, Markov transition process, where we were able to evaluate that given a current operating point, what is the likelihood of moving to the next point. And essentially, we were able to design a tool which forecasts errors in an adversarial manner for wind, but at the same time, it conditioned it by the current operating point. And that led to the ability for us, for a given forecast, to have conditional error forecasts and produce adversarial scenarios with a confidence range shown here. In general, the rule is that the greater your confidence range, the more reserve you will have to provide, because you would expect greater variations in the wind power outputs. But here we were able to reduce this range in some cases or estimate it more carefully because of this conditioning on the current operating point. So essentially, you can still that even if you do this job, even if you try to narrow down the range of flexibility that wind power outputs can provide, you will still see quite a bit of variance in the system, right? And this is essentially the residual variance that you would like to embed into the system, right? But the problem is that we assume we have this data, and we don't always have data. And when you don't have data, you cannot use this sophisticated methods. You have to use number crunching essentially to come up with data. And when we start looking into that, we designed what is known as a GAN, a neural network which includes two neural networks, actually, generator and discriminator. And the objective of the generator is effectively to produce a sample which is going to be indistinguishable with a certain threshold from the real data. And that's a fairly well-known framework for data generation, which we expanded on by integrating a power system model, because we wanted to generate system adversarial scenarios which would not be part of the general model, but would be part of the system model. So we wanted to have a ranking mechanism to evaluate how expensive this data would be for the system. And that also worked out. We got the data, which also internalized the severity of the impacts on the power grid. And using this data and the historical data that we were able to analyze, we were prepared to model variance in unit commitment and optimal power flow, which are the two problems which system operator and market operator solves in order to get a solution to the problem. So the idea is very simple, that right now, instead of a deterministic forecast, which we denote as PU, power of the uncertain resources, whether it's wind or solar, we have PU plus some omega, which is an error. And basically, we assume that all conventional generators, they must compensate for this error. So their power output is the deterministic output minus alpha, the response coefficients, also known as automatic generation control, which varies from 0 and 1, times the total system uncertainty, which is computed as vector of ones transposed multiplied by the vector of uncertainties.
Why the sum of alpha I equal to 1?
That's a good question. So what we make sure is that when you enforce this condition, we can prove that the total response of all generators in the system, if you sum the left-hand side here, is going to be sufficient to compensate for the uncertainty of renewables if you sum up the right-hand side here.
Okay.
So it's essentially a condition which ensures sufficiency of reserve available in the system from conventional generators.
So I is an index of the generator.
Yes, I is an index of generator, you're right. In this particular setup, we also have the chance constraint on power flows, when we basically say that the likelihood of violating power output limits on generators and voltage magnitudes and the power flows should be fairly small, where small is defined by user-defined parameter epsilon. In other words, we want to make sure that these constraints hold with a very high probability by setting epsilon to a very small number. And essentially, by using the selection of omega, uncertainty that we have, and epsilons, we can ensure that the formulation is such that the physical risks are counted in these formulations, the risk of constraint violation. At the same time, this formulation can be reformulated into a convex optimization problem. So what we did next, we investigated how this was possible to produce adequate electricity prices. And essentially what we did, we basically internalize the objective and we robustify it against the uncertainty by using the expected value operator. And we basically figure out the way to do that by minimizing the cost of the power production of conventional generators and the cost of reserve provision, which is quadratic in term S, which is nothing else but the cost of uncertainty because S represents the system-wide variance, right? So in this case, what we were able to do, we were able to reformulate a traditional UCOPF problem as something that is cognizant of the variance which is present in the system.
So the first objective function is a maximization objective. And then you equivalently transfer to a minimization objective.
It's a typo. Actually, the first one.
The first one should be also minimization.
Yeah, it should also be minim. Okay, typo. Sorry.
Sure, no problem.
Okay, let me put it here to avoid confusing people. Yeah. Okay. Sorry. Thank you for catching this up. Yeah. Yeah. It's minimization. Yeah. Okay. Yeah. Now it's correct. Mm-hmm. But the important point here is not actually the typo, but thank you for bringing this up, but the fact that instead of expectation, we can use any risk measure you want. You want to use value at risk, be my guest. You want to use conditional value at risk, be my guest. You want to use some percentile risk. As long as you have a tractable reformulation, which is going to yield a fairly convex formulation, then you can use it. So we were playing around with this formulation and we were able to show some very interesting results. That when we derive the price for active power, lambda P, and reactive power, lambda Q, at every location I, we will see that it will depend on the cost coefficients of the generators and dual variables of the binding constraints. The same.
How do you derive these results? You derive the KKT conditions?
Yeah. Okay. Yeah, so I'm omitting the procedure for derivation because it's like a little bit of algebra there, okay. But it's in the paper, yeah.
Okay, and the result one, the lambda here, lambda REP is the active power price. So it's equal to PGI. I suppose it is the active power output.
Yeah.
Plus alpha I,
VI.
These are the cost
coefficients. Yeah.
Coefficients. So, and then we have the dual variables, delta I, P. Okay. So I'm wondering why this price, lambda I, will be relevant to the active power output, the PGI.
It is kind of property of the blocks because as the power output changes, availability of resource changes. It's like an intersection of the supply and demand curve.
Okay.
When you change your P, right, from the viewpoint of a market, you either add resource or you subtract the resource, right? So the price would change proportionally. It's a monotonic behavior that you would expect in this case. And keep in mind that the costs here are quadratic, not linear. If you had linear costs, then yeah, it would go away. P would go away here if you have a linear costs.
Okay.
On the other hand, when we derive price for the reserve, we observe that it depends on S, which is nothing else but the sum of system variance. The more variance you have in the system, the greater reserve price you will have. And zeta epsilon, which is a parameter representing the sensitivity towards the selection of parameter epsilon, which defines violation tolerance of chance constraints. So essentially, taking the prices lambdas and the price key, we can show that these prices are efficient and will constitute a competitive equilibrium. And at the same time, if you consider no binary decisions in unit commitment problem, because the problem is convex, this outcomes of this chance constrained market that we proposed would ensure revenue adequate and cost recovered results for a given risk measure. We also
revenue adequacy and cost recovery. These are the requests for market design.
Yeah. And the important thing is that these two results that we were able to show in our result 3, they will also hold for the case when we have a distributionally robust case. Basically, when uncertainty omega is not given by a distribution, but given by a family distribution or by some other uncertainty set that we can internalize. And that is a very cool result because there are two ways to ensure that we can solve a distributionally robust problem of that size. One is based on the analytical reformulation developed by Shi and Shabir Ahmed in 2019, and the other, the work that was done in collaboration with Miles Lubin and Scott Beckhouse at Los Alamos National Laboratory, where the solution was algorithmic. But basically, when we apply it to ISO New England, and we analyze how the prices would change for different wind penetration levels, right? And this column represents 2% penetration level, this column represents 10% penetration level, and this 20% penetration level. We will see that as the value of epsilon reduces, so we become more conservative in our optimization problem, the energy prices, they will tend to increase for all the chance constraint approximation that we're using. As you can see, value for the reserve price, it will increase much stronger, right, than as compared to relative energy prices, right? And that is exactly the kind of result that we want to show, that the energy price, the power price up in here, is going to be less dependent on uncertainty than the reserve price. So effectively, we decouple the two, right?
So the reserve price is it can rise, let's say, for several times. I mean, with the increase of the parameter epsilon, which is the chance constraint parameter here. And then on the other hand, the price for lambda, the power price, only rises like very slightly. And the important thing is that it may look like, you know, unnecessary math, too much proofs, which will never get implemented in practice. But the interesting thing is that if we look into what other companies do in reality, they already do it. They just don't do it endogenously, they do it exogenously. For example, Swiss market operator, they set up reserve constraint based on probability requirement equal to 99.8. So their sufficiency of reserve is 99.8, which in our case will roughly correspond to 0.2% of epsilon, right? Yes, they set the parameter epsilon to 0.2. Yeah, okay. They don't include it in the market. They do it outside of the market, right? But they essentially lose the optimality because of that. In America, very simple, very similar procedure is employed by ERCOT, right? Which is used 98.8 percentile for setting up their reserve requirements. So what we develop, it's not a very far distant connection to the real world practice. It's an improvement of the real world practice. Another idea that came into mind is that if we penalize the variance of uncertainty in the objective function with the cost coefficients, as we presented on the slide where you discovered the typo, where there should be minimization versus maximization. Another thing would be to look into the structure of these chance constraints, right? And if we reformulate these chance constraints, we will see a very interesting property that a linear reformulation that we obtain here is nothing else but a combination of the mean value, which you will get in your deterministic solution. This is your limit, right? And these two terms, they represent standard deviation, T, right? And some risk coefficient. Basically, what happens is that by adjusting epsilon, I change coefficient Z, right? And that changes the adjustment, the fraction of variance that I need to add to my mean solution and remain within this thing. So essentially, the idea here, if we already have this T, which is this
rather big term over here. It looks monstrous, but it's nothing else but the variance of a state variable. How come if we devise this variance term for all state variables, right? We can devise it for reactive power here, for voltage here, and for power flows, active and reactive power flows here, and then penalize it in the objective function. So the penalty factors, which are large p's, right? These are user-defined parameters. But basically what will happen is that along with finding the optimal solution, you can also reduce the variance. So basically how much deviations you would expect from each state variable. And the interesting thing that normally in the financial sector, this kind of penalties, this kind of variance minimization penalty, it comes at a great cost. But if you look at in our particular example, you will see that the cost does not change much. We vary the penalty psi in a fairly large range, right? Between 0.1 and 1,000, right? In appropriate units.
This is for all the terms.
Yeah, for all the terms. Yeah.
Voltages, active power, reactive power.
Yeah.
Okay.
And you can see that the price, the total cost, does not change much. It changes by 0.03%, which is fairly small. At the same time, we see that the reserve price here, right, increases by 5 times, right? Which basically shows that if you reduce variance, if you penalize variance heavily, right, you have to incentivize resources that provide you flexibility and reserve. So the other interesting thing is that with this fairly small change in the total cost, which is like 0.03%, you manage to reduce fluctuations of the system variables, the variance of the system variables, state variables, quite a lot. In some cases by almost 100%, right? So variance reductions comes at very zero cost and help you to incentivize flexibility providers.
Yury, have you tried to use different, let's say, penalty coefficients? We
tried for different variables, right? But the difference in cost was not that great because, like, you know, when you vary it between 0.1 and 1,000, right? And it doesn't affect the cost. It just doesn't make sense to increase fidelity and target it. But it was like numerical difference was very small.
I see.
But basically what turned out is that we were able to control the variance in the system, and you know, the difference did not affect the interconnection, right? So what you can see here is the price, active power price between the variance aware solution, where we penalize variance, and the deterministic solution, right? And you can see that only a few nodes here and here were affected and showing any difference, right? So another point that we're trying to make here is that penalization of variance will not affect the majority of market players. It will help you to point out the troublemakers, the entities which create the variance for the entire system. Yep.
The previous slide, you plot the price for different areas together with the IEEE 118 bus, the grid topology. How you plot them together?
How do what?
Yeah, how you visualize this result?
Python pipeline. Yeah.
I'm very impressed by this. Impressed by this plot because it shows clearly the price variations and also the topology of the grid. And then if we check the price difference, the price valleys and the price peaks between node 20, 23, 24 here. So there's a congestion line, heavily congested between 21 and 22.
Yeah.
You have shown here.
And I just want to make one more comment. Thank you for acknowledging the quality of the figures, but the credit should go to my postdoc, Robert Meath, who will be very happy and very pleased to hear that you recognize because he spent a lot of time on this particular figure.
Yeah, I can imagine. This is very
it's Robert's talent. So basically, the question is, what is the problem with the current market? And what we did here, we essentially decomposed the problem that we solved in a very simplistic form between the problem of the market, and the market want to make sure that it balances the power produced by conventional generators and the uncertain generators equal to the demand at every node of the system, and reserve adequacy constraint, right? You'd also want to make sure that the problem of the conventional generators here, right, is done. So basically generators get paid for the power they produce and for the reserve they provide, right? Subject to some constraints that they have, right? The problem with generators, with the current market, comes when we attach to the renewable generators, because right now in the current market, they are only paid for the power they produce, and they are not penalized for the reserve that they cost, right? And because of that, because the current market don't have this mechanism, we'll always end up not an equilibrium solution that we should be at, right? So from this viewpoint, if we perform this autopsy of the current market design, the lack of penalty for renewables to adhere to a given market strategy is the main bottleneck. So there is a paper of Ben Hobbs and Lin Deng on what is the cost of negative bidding, right? And that is exactly the paper that answered this question, what happens if that occurs? And it's not a question of market design or any engineering concern. It is really a policy question, whether we want to penalize renewables for deviating from their forecast production, from their position in the market. And for many years, we said, no, we don't want to do it because we want them incentivize their participation, right? We want more renewables. Right now, when the problem becomes more prominent, we would like to make sure that it doesn't do that. But in the future, it needs to be reconsidered, and particularly it needs to be done in a case when they will have a way to hedge the risk. And that leads to the final chapter of this presentation, when we're going to discuss the transition from variance assessment and the union commitment OPF problems to financial risk trading. And the idea here is very simple, that right now, chance constraint market assumes risk neutral behavior. We minimize expectations, right? And it's more likely that modern market participants will be risk averse, in a sense that they will value avoiding losses greater than making money. And in this case, we essentially derive a very simple formulation for a risk averse market participants when we minimize the worst case costs for them under the worst case realization of the uncertainty given from this set, right? Where this set assumes zero mean assumption on the uncertainty, but it assumes also a certain variance. And from this viewpoint, we introduce a mechanism for risk trading, which is called RO-Debro security. It's a very classical instrument, which is very helpful for risk trading analysis. And what we wanted to achieve with them, we wanted to incentivize more flexibility and system beneficial behavior. So essentially what we did here was said that if any producer without distinguishing conventional or renewable seeks to receive a payment, AI, for all possible realizations of uncertainty omega, it must pay this price to the market. So essentially it's like an insurance mechanism, right? And another important thing, that all of those securities, AIs that we have in here, that must be balanced, right? So if I buy an insurance as a market participant, there should be someone else who sells this security to me. So we were able to show that, in particularly, the price of this last constraint that we have in here, the dual variable, right? It's also the worst case distributional property. So essentially what we can show is that it's the measure of the worstness that we're adopting here. Another important result that we show is that the residual market risk will be an intersection of individual uncertainty sets of market participants. And just to show this in a very toy example, when you have 5 producers and you have 8 future states, right? We were able to show that this system is balanced and it produced adequate results from the viewpoint of risk positioning in the market.
But here, sorry,
sure.
Previous slide. So mu here is ADS optimum price, as you have mentioned. So you have mu1 to mu8.
Mu1 to mu8.
In the x-axis, yeah, in the bottom graph, yeah. So what does it mean? It means you have different market clearing results?
No, what that means is that you have entities that buy securities and you have entities that sell securities, right?
Okay.
Negative means that you are selling, and orange means that you are buying, right? But you buy it associated with every particular state, right? Discretized state omega. Okay, so the price is not associated, the price is not uniform for all states, right? The problem here is that solving this problem at scale requires far more boosted results. And for this, we will employ machine learning, right? And machine learning applications in the power system domain are very complicated because we want to devise ML which is explainable and trustworthy. So we want to use some intuitions. And luckily, when we move from this system, from this small system here, right, to something realistic, which has 1800 nodes up in here, right, we have one property which we observed everywhere, that there are going to be very few binding lines. And here you have a snapshot from New York ISO, when at a single instance of time, you only have a handful of transmission lines which have non-zero dual variables. And that practically means that these are the only congested lines. What that means is that you can throw in power flow limits for other lines and enforce transmission limits of these lines as equality constraints. So in this particular case, what we need to do in order to speed up computations is to design a way to guess which lines are binding ahead of time. And what we were able to do in this work, working with our colleagues at Arizona, University of Arizona, is essentially to map load vectors into binary decisions where they define whether upper or lower flow limits are binding, 0 or 1. And from this viewpoint, we were able to design this loss function. And the interesting result is that after that, we essentially can reduce our optimization problem to a very simple set of linear equations and solve them. And here is an example of the system. As soon as you get it, you can solve it for guessed combinations. And interesting,
you pick up this binding lines constraints.
Yeah.
And then you can reduce it to, I mean, in the KKT systems, you can reduce these equations. And this way you can reduce the number of equations in the KKT systems, solving QPSOC.
Yeah, precisely. But the interesting thing that we recently discovered is that neural networks, they're notorious for their lack of guarantees. And what we were able to show, that if we adopt the support vector machine, we can bound the empirical risk to the number of training samples used in this neural network, right?
Is this result derived by you? I mean, this guarantee?
So we showed how this results. So in general, empirical risk, it comes from the work by Vapnik, right? For support vector machine, but what we did here, we derive it for the particular case of optimal power flow. So we did not invent support vector machine. Unfortunately, it was someone else. And then basically we were able to show how that works. And, you know, one conclusion is that it's very specific to the unique commitment case. But as you can see here in configuration 1, we got a very high degree of accuracy. In other case, we got 75% accuracy for the difference between the predicted dispatch and predicted LMPs.
So this here you show the accuracy for the performance of your methods. So what is the fraction of samples? I mean,
I think it's about 1,000 or 10,000 samples. I don't remember the number off the top of my head.
So that is data you used to train the SVM, or?
Yeah, that's the data that we use to train the neural network. SVM comes only after when we want to get guarantees for the samples.
Okay. So what is the meaning of the different color of the
different colors are different noise. Yeah, different levels of exogenous noise.
Okay, which is a parameter in the training.
Yeah. And sorry.
Okay, and then in the y-axis we have the max delta
LMP.
Price.
Yeah, it's basically prediction error that we achieve with machine learning relatives.
So the benchmark is solving the model in conventional way. Okay.
So basically going back to where we started, right? Bill Gates and Al Gore, right? The idea is very simple that what we develop fits into this model, right? And in particular, it helps to deliver clean electricity from the points where it's being produced to the points where it's going to be consumed and it will replace the fossil fuels. But we're looking into a broader picture. What we really want to see, we want to see how it contributes to the entire economy. And we want to create a model that is going to account for stochastic market case as it would deliver value to various sectors of the economy. And we're looking into the benefits of electrification for the economy through the stochastic market design. And this is something that we will achieve by connecting the stochastic market model that we have here to the computable general equilibrium, which basically represents the sensitivities of different economic sectors to the electricity sectors and to cross sensitivities of one another. So essentially, just to reiterate the conclusions of this presentation, electrification hinges on the ability to leverage various technologies, and the market provides an opportunity to treat them on a par. It doesn't matter whether it's solar, wind, or conventional generator, as long as you have uncertainty in your percent risk for the system, you're going to be treated equally. And the way to enable that, in our opinion, is through chance constraints by using the variance as a way to connect uncertainty to risks. And chance constraints help us to map technical risks, such as constraint violations, physical risks, into financial risk, basically how it projects into prices and into the reimbursement of payments. And it provides an interface for risk hedging and risk trading by market participants. For us, machine learning, it's more than just a prediction tool. We believe that it can be a very efficient tool for enabling market operations under uncertainty. And we believe in explainable and trustworthy AI that will help us to devise incentives, to embed ad hoc engineering rules that exist right now into the decision-making stages and to provide explanation to the results that this market will encourage. Okay, at this time, I would like to say thank you so much for your attention. And if you have any questions, just send me a short email.
Yeah, thank you. Shall we?
Yeah, thanks.
Thank you very much.
Thank you.
Yeah, if you have any questions, we can also discuss.
I'm kind of curious about the amount of wind energy in the US, for example, in New York State. Is there already a large buildup of wind energy?
So it's very non-uniform across the country. In New York and Iceland, England, it's fairly small. It's about 2-3%. Sometimes it goes probably 5 tops. In some parts of the country, like Midwest, it's like, in double digits. California is big. Pacific Northwest is big. Texas is very huge on wind. Yeah, so there are renewables, but America is an extremely diverse country. In a sense, I'm trying to find it because actually that's something that I teach last semester. Okay, you'll have to trust me without a slide, okay? America, the strength of America is in its diversity, that there are regions in the country which are rich for wind. There are regions in the country which are very rich for solar. So the southern part of the country, like, Florida, Georgia, Alabama, parts of Texas, all basically everything around the Gulf Coast, right? Then Southwest, Arizona, right? Nevada, New Mexico, they're very ripe for solar installations. Texas is very ripe for wind, right? Midwest, it's basically the wind capital of America, right? Midwest has gigawatts of the capacity installed. California, Oregon, Washington, the entire West Coast, right? They're very good for wind. And both the Atlantic and Pacific are very rich for the offshore wind potential. Atlantic coast, Massachusetts, New York, New Jersey, these are the leaders so far, but very soon we see projects being gradually getting up to speed in California too. on the West Coast. So offshore is going to be very big in America as well. Plus, you have this examples of wonderful places like Alaska or Hawaii, where you have very high penetrations of renewable energy simply because they are isolated from the rest of the country, and transporting fossils over there is far too expensive. Another example that America could be somewhat proud of, America could have done a better job, but considering all the limitations, it fares decently well. In that regard is Puerto Rico, which is not a state, it's still a dependent territory. But essentially, after the hurricane, which happened almost 5 years ago, wow, time flies, they're rebuilding the power grid over there, and sustainability, it's a major emphasis towards it. Of course, America is far behind, for example, Denmark, right? Or even Germany, but it's a very different country with very different landscape.
How is it with, you mentioned those areas with highly solar power generation and the areas like Texas with wind generation. How is it with transmission between those areas?
Okay.
Is it
good
or is it strong? Or?
So if you think about the power grid in America, essentially it's broken down in 3 pieces: Western interconnection, Eastern interconnection, and Texas. And within each of these 3 buckets, transmission is decent, but between these 3 buckets, transmission is very bad, right? In the long run, it may prevent America from taking advantage of energy arbitrage across different parts of the system with complementary technology. For example, when solar fades out in the evening, wind tends to increase the production. So there could be a nice complementarity when one source adds to the fading one. But yeah, that might be an issue. A very interesting problem is to basically see how the entire American power grid could be put together in one large grid, like for example here in Europe or in China or in some other countries. But it's a big consideration because it's a lot of engineering work, it's a lot of regulatory work, and in some cases it runs into locational specifics.
Yeah, that's quite true. It's very different from Europe and China. In China, it's more centralized planning and operations, and the grid codes for the entire China is the same one set of grid codes for everyone to implement. So everyone comply to one standard. And in the US, I don't know, maybe the different regions, they have this very different specifications even for the grid codes. Even for traditional operations, not less to mention the differences in the integration of renewable energies. They have different resources, different considerations for the local resources that we hold in different regions.
Mm-hmm.
Do you know if there is much high voltage DC transmission?
There are some, and they're going to be more. But so far it's underdeveloped as compared to Europe, in part because there was never drive to basically put the system together. But yeah, HVDC, there are some examples that exist there. For example, the so-called Pacific Intertie, which connects hydropower plants up north in Washington to California. And it's motivated there not by the integration ability, but rather by the fact that they need to deliver a tremendous amount of power across a very long distance. So building HVDC makes economic sense. I believe Pacific Intertie was not built for any kind of integration reasons. It was built for purely economic reasons. There are also projects like San Francisco Bay Cable, which basically connects different parts of, it's a underwater cable. It's also DC. I also think there is a cable in Long Island Sound connecting Long Island and either Connecticut or New York. No, it's Connecticut. and I think it's also DC. So there are some DC projects, but it's not as massive deployed as elsewhere.
There are some discussions here that to connect Iceland with HVDC to, for example, the UK. That would be a tremendously long cable.
What's the distance?
If I remember correctly, was it 1,200 kilometers?
1,200
kilometers. I see some feasibility studies for this connection between Iceland and UK, and also even Iceland and Norway on the European continent. Iceland, we have abundant, energy resources.
We should have.
Yeah.
So if we take a look at the map, will Iceland be closer to Europe or to Canada?
Closer to Europe. That's closer to Europe.
Okay. Okay. Closer to Europe. Okay.
I mean, flying from here to London is just under 3 hours.
Okay.
Flying to Boston is 5 hours.
Okay, I see.
Would be some also feasibility study for the connections between Iceland and Canada, or even New York.
Do you know if Greenland? Do you know if Greenland is connected to Canada?
I don't know.
Because that would be my best bet. That looking at the map, it's closer to
I
Greenland.
just know from the telecom connections that there's an optical fiber called Greenland Connect. It's very problematic because it's on the ocean ground, and then come the chunks of ice, and they can strand.
Oh, okay.
And cut the cable. That has happened. So it's very difficult.
I see.
With submarine cables around Greenland.
I see.
They have to dig it into the seabed.
Okay.
Under the seabed.
Yeah. And maybe that's not enough. I don't know. But the Greenland Connect cable has been very problematic. It's a pity for Greenland. If it's cut, then there can be an outage of months.
How many people live there?
In Greenland? It's about 50,000.
50,000. Yeah, it could be a significant issue for them.
Okay. Let's see if we have some questions from the online attendees in the chats.
Iceland has scored a goal, so we can be happy about that.
Let's see. Yeah, one note, and it's second time.
Yeah.
Second half time. No questions?
I don't think we have
questions.
Then thank you again for organizing this all. It's been fun.
Welcome.
And next time, I promise I'll be better in communication to make sure that we find a better date.
I mean, this